Hey guys, Mr. B here, and in this video we're going to be going through the chapter 12.1 practice problems. Alright, so beginning here with number 1, it says Tiny Trike has decided to make 288 tricycles each day. How many tricycle seats, wheels, and pedals are needed? Okay, so in order to answer this question, we are going to need to use the chemical reaction for making a tricycle, which was given to us in the notes. So I'm just going to copy and paste this down here so we have it. Okay, right there. And we'll just make this a little bit smaller. Okay. I'll probably bring it down. There we go. So you can actually read the problem. That would be good. All right. So we are being asked here to figure out how many seats would be needed, how many wheels would be needed, how many pedals would be needed for 288 tricycles a day. So looking at the reaction, there are, of course, coefficients in front of some of these things. So basically, if we look at seats to tricycles, we need one seat to make one tricycle. Okay, that's, you can see in front of the S that there's no number. That's a 1. So one seat would make one tricycle. So it's a 1-to-1 ratio, which means that if we wanted to make 288 tricycles, we would times this by our conversion factor of 1 to 1. Okay, one seat over one tricycle, and we essentially are just going to get an answer that's exactly the same as the amount of tricycles that we have to make, right? So we need 288 seats because we're essentially just taking 288 times that by 1, divide that by 1, right? It's a 1-to-1 ratio. So that one's pretty simple. For the second one, for wheels, we can see that in our reaction, we need 3 wheels for every 1 tricycle. Okay, so that's a 3-to-1 ratio, which means that if we wanted to make 288 tricycles, we need to multiply this by 3 wheels per 1 tricycle. So we're going to times this by 3, essentially, right? It's a 3-to-1 ratio. Let's make their font a little bit smaller here, too. There we go. Okay, so if we take 288 and times that by 3 over 1, or just essentially times that by 3, we get 864 wheels. So we need 864 wheels to make 288 tricycles. And then lastly, for pedals, we can see that we need 2 pedals for every 1 tricycle. Okay, so 2 pedals for every 1 tricycle. So if we set this math up, again, using dimensional analysis, we're going to multiply this by 2 pedals over 1 tricycle. So 288 times that by 2, and we get 576 pedals are needed. Okay, so that's all they're asking for us to do in this problem. They basically just want us to interpret the reaction in terms of different materials. All right, taking a look at number 2, it says an apple pie needs 10 large apples, 2 crusts, top and bottom, and 1 tablespoon of cinnamon. Write a balanced equation that fits this situation. How many apples are needed to make 25 pies? Okay, so first up, we are going to write the chemical reaction based on the description they're giving us. Okay, so it says an apple pie needs 10 large apples. So we'll go 10 AP for apples plus 2 crusts, so 2 CR, plus 1 tablespoon of cinnamon, so 1 CI, and we don't need the 1, I guess. And that will make us 1 PI for pi, which we don't need the 1. Okay, so here would be like our balanced chemical reaction, again, based on the description they're giving us in the problem. We need 10 large apples, 2 crusts, 1 tablespoon of cinnamon, and this will make us 1 pi. Now the question asks, how many apples are needed to make 25 pies? Okay, well, let's look at the ratio between how many apples are needed per pie you can make. So it looks like every 10 apples that we have, we can make 1 pie. Okay, that's what it says in the reaction. 10 apples, 1 pie. So if we have then 25 pies to make, how many apples are we going to need? Well, this is a conversion factor. Okay, we can write this as a fraction. 10 apples over 1 pie. And all we need to do then is, of course, set up our dimensional analysis to cancel out the unit of pies and get into the unit of apples. So 10 apples over 1 pie, like this. If we do that, our units of pies will cancel and we'll be in the unit of apples. And essentially all we're going to do is take 25 times 10. So 25 times 10, and we need 250 apples to make 25 pies. Okay, there you go. All right, moving on to number 3. 2 moles of potassium chloride and 3 moles of oxygen are produced from the decomposition of 2 moles of potassium chlorate, which they're giving us the chemical formula for. Write the balanced equation. How many moles of oxygen are produced from 12 moles of potassium chlorate? All right, so there's a lot of information, a lot of stuff here, okay? So let's just kind of read what they're giving us. They do want us to write the balanced equation. So we have to write a reaction. We're going to have to probably write it from the information they're giving us. So it says 2 moles of potassium chloride and 3 moles of oxygen are produced. Okay, so those are our products. So 2 moles of potassium chloride. Okay, now potassium chloride is KCl. I'm not going to go into how do I write that chemical formula. We learned that in chapter 9. We did that again in chapter 11 when we were writing chemical reactions. So at this point, you should know how to write chemical formulas. If you're still struggling at this point in the last chapter of the course, then you should be asking me for help to help you. But I'm not going to go over how to write chemical formulas in this one. So we have 2 KCl, okay, 2 moles of potassium chloride. We're going to put a 2 in front of the KCl. 3 moles of oxygen. So 3, and oxygen is diatomic. It is a Brinkelhoff. So it's O2, not just O. Okay, so those are our products, and those are being produced from the decomposition of 2 moles of potassium chlorate, which they are giving us the chemical formula for, which is KClO3. Okay, so this is essentially our balanced reaction based on the information they're telling us. 2 moles of potassium chlorate break down to make 2 moles of potassium chloride, 3 moles of oxygen. Okay, now the question or the problem is how many moles of oxygen are produced from 12 moles of potassium chlorate? So we are essentially taking 12 moles of KClO3, and they want us to tell them how many moles of O2 can we make. So to do that, we're going to need to know, well, what is the conversion factor between moles of potassium chlorate and moles of oxygen? And that's where the coefficients come into play. Okay, so this reaction here is like our recipe. Okay, it tells us how much of everything we need for this recipe to work. So 2 KClO3 means that for every 2 moles of potassium chlorate that we use, we will make 3 moles of O2. Okay, so for every 2 moles of potassium chlorate we start with, we'll make 3 moles of oxygen. That is the ratio. It's a 2 to 3 ratio. That also can be written as a fraction. So 2 moles of KClO3 for every 3 moles of O2. Okay, you can write it as a fraction. And once, of course, we can write it as a fraction, then from there, this basically is just a conversion problem. We're just converting moles of KClO3 into moles of O2. And our conversion factor is given to us. So we just got to set up our dimensional analysis to cancel out the right units. In this case, you want to cancel out moles of KClO3, and you want to be left with moles of O2. Okay, so we're going to set up our math like this. That way, moles of KClO3 is what we're starting with, and we have moles of KClO3 on the bottom of our conversion factor, so that will cancel. And basically, we're going to take 12, multiply that by 3, and then divide that by 2, and I get a final answer of 18 moles of oxygen is how much we can make. And there we go. Okay, so it's pretty much a lot of the stuff that we've already learned in chapter 10 with converting and in chapter 11 with writing chemical formulas. We're just kind of putting them all together. All right, number 4, it says balance the following equation and then interpret the balanced equation in terms of relative numbers of moles, volumes of gas at STP, and masses of reactants and products. Okay, so first we got to balance this equation. All right, so I'm going to rewrite it here down below just so that way we can balance it. Okay, so C2H2 gas plus O2 gas makes CO2 gas and H2O gas. Okay. All right, so there's our reaction. In terms of balancing, let's take a look. So we have 2 carbons on the left. We have 2 hydrogens on the left. We have 2 oxygens on the left. Okay, so that's all the stuff we have on the reactant side. On the product side, we have 1 carbon. Hydrogens, we have 2 hydrogens right there. Okay, so there's 2 H's. And oxygen, we've got 2 oxygens here plus 1 oxygen there. So total, that is 3 oxygens. Okay, they're in 2 different places, but total, that's 3. Okay, so already off the bat, we can see the carbons are not balanced. So let's balance the carbons first. So we're going to need to put a 2 there. That will multiply the carbons by 2 and turn this into 2. All right, so those now are balanced. For hydrogen, hydrogen's already balanced, but oxygens. Okay, now we put this 2 here. That is going to multiply these oxygens here by 2. Okay, so 2 times 2 will give us 4 oxygens right there, plus the 1 we already had here on the right. So that's now going to be a total of 5. Okay, now the carbons are balanced because we put a 2 there, and our oxygens, however, are not balanced, but we haven't really tried to balance them yet. Hydrogens are still good. All right, so now we got to fix the oxygens. Okay, now this is where it gets a little bit tricky, so I'm going to show you, again, a trick to do this. We have 2 oxygens on the left. We have 5 on the right. We could multiply this by 2.5. Okay, so if we go 2.5 times 2, that will give us 5 oxygens on the left to balance out the 5 oxygens on the right. Problem, of course, is that we can't actually keep it as 2.5. Okay, so you can't have half of an oxygen. But what we can do is once we have this there, then in order for us to fix this so it's not a fraction and still have everything be balanced, is we just double everything. Okay, so originally there's a 1 in front of that compound in our reaction, even though it's not written. So if we were to double that, that would become a 2. 2.5, if we double that, that would become a 5. This originally was a 2. If we double that, that becomes a 4. And here, again, there's nothing written, so technically that was a 1. But if we double that, that also then becomes a 2. Okay, so now let's recheck to see if things are still balanced. So here for carbon, we have 2 times 2. That is 4 carbons. We have 2 times 2 hydrogens. So that is 4 hydrogens. And we have 5 times 2. That is 10 oxygens. Okay? On the right-hand side, we have 4 times 1 carbons. That's 4 carbons. All right, so those are balanced out right there. Hydrogen-wise, we have 2 times 2, so that's 4 hydrogens. Okay, so that's balanced right there. And then for oxygen, we have 4 times 2. Okay, so that's 8 oxygens right there. And then 2 times 1, that's 2 oxygens. So we have 8 oxygens here, plus 2 oxygens there. 8 plus 2, that's a total of 10. And there we go. Everything is balanced. Okay, so here is our balanced equation. And now we have to interpret this in terms of moles, volume, which is liters, and mass, which is grams. All right, so let's do moles first, okay, because that's pretty easy. The numbers, the coefficients we just put, those are moles. Okay, so basically 2 moles of C2H2 plus 5 moles of O2. Okay, so we can see here that again, 2 moles, that's what the 2 is. Okay, that's moles, 2 moles. 5 moles, okay, right there. We'll make 4 moles of CO2. And we'll make 2 moles of H2O. Okay, so interpreting an equation in terms of moles is very easy. We can just look at the coefficients. All right, well, what about volume, right? Liters. All right. A little bit more challenging, but not that difficult because we have learned how to convert between moles and liters. So the conversion between moles and liters is molar volume. 1 mole of anything at STP is 22.4 liters. Okay, so basically all we need to do then is to take our 2 moles of C2H2, okay, it's 2 moles of C2H2, and multiply that by 22.4 liters. Which then will give us 44.8 liters of C2H2. So the 2 moles of C2H2, that's 44.8 liters of C2H2. So there's that one. For oxygen, we'd take 5 moles of oxygen, times that by 22.4 liters. And that will tell us our oxygen ones, which I'll need to do a calculator for. So 5 times 22.4. And we get 112 liters of O2. Okay, so there's our volume for the O2, 112 liters. The CO2 is 4 moles. So 4 moles times 22.4 liters. So 4 times 22.4. That is 89.6 liters of CO2. All right, so 89.6 liters. And then lastly, we have, again, 2 moles of H2O, and times that by 22.4 liters. And so that is 2 times 22.4. That is 44.8 liters of H2O. Okay, so there we go. There is all of our stuff in terms of liters. Okay, we just got to do a little bit of multiplication. And then lastly, in terms of mass, to do mass, we'll need to know the molar mass of all these materials. So this one is going to take a little bit more work. But for each material, we just got to find their molar mass. So C2H2. So carbon has a molar mass of 12 grams. I'm not looking at a periodic table because I know this off the top of my head, but you need to look at a periodic table to find this number. Okay, so 12 grams for the carbon. Hydrogen has a molar mass of 1 gram. Now there are 2 of them in this compound. Okay, so you got to times this by 2. So that's 24 grams. And there are 2 hydrogens in this compound as well. So you got to times that by 2, and it'll get 2 grams. Okay, so if you add those together, that means that C2H2 has a molar mass of 26 grams. Okay, so every 26 grams of C2H2 is equal to 1 mole. Okay, so 1 mole of C2H2 is 26 grams of C2H2. And we have 2 moles here. Okay, not 1 mole. We have 2 moles. So instead of having 26 grams, we're going to take our 2 moles and take our 26 grams and times it by 2. Okay, because we have 2 moles. So just times it by 2. And 26 times 2, that is 52 grams. So we have 52 grams of C2H2. Okay, so there's that first reactant. There's its mass. All right, O2. So oxygen has a molar mass. I'm going to do it over here. Okay, so oxygen has a molar mass of 16 grams. There are 2 of them here. Okay, 2 of them. So that's actually going to times that by 2, which means for O2, we have a molar mass of 32 grams. And we have 5 moles of O2. Okay, so again, 1 mole of O2 is equal to 32 grams. But we have 5 moles, so we got to multiply that by 5. Okay, so we're going to take 5 moles, put this in parentheses here. Okay, 5 moles times that by 32 grams, and that will get us our mass for the O2. So 5 moles times 32, that is 160 grams of O2. Okay, 160 grams of O2. So there is that mass. All right, for CO2, carbon is 12 grams, and oxygen is 16 grams. Make sure we get down here. Okay, so oxygen is 16 grams. And there's 1 carbon, but there's 2 oxygens. So we got to times this one by 2. Okay, so that's 32 grams. And then if we add those together, okay, 12 plus 32, that gives us a total of 44 grams. So CO2, okay, so 1 mole of CO2 is equal to 44 grams. Okay, that's its molar mass. And here we have 4 moles of CO2. So we're basically going to take 4 moles of CO2, 4 moles, and times that by 44 grams to get the mass of the CO2. So 4 times 44, we get 176 grams of CO2. Okay, so there's that mass. And then finally, lastly, we have our H2O. H is 1 gram, and our oxygen is 16 grams. 16 grams. We do have 2 H's in H2O, so we got to times that by 2. Okay, so that's 2 grams. And then if you add those together, that gives you a molar mass of 18 grams. So H2O is equal to 18 grams. Okay, so 1 mole of H2O is 18 grams. We have 2 moles of H2O, so we got to times that 18 grams by 2. Okay, so 2 moles times 18 grams. So 2 times 18. This gives us a mass of 36 grams of H2O. Okay, so there is all of our material now in terms of mass. And I know that one took a little bit to do, okay? So hopefully that makes sense. All right, moving on to the last problem here, number 5. 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 moles of water. How many moles of water are produced from 2 times 10 to the 23rd molecules of oxygen? How many moles of water are produced from 22.5 moles of oxygen? Okay, so there's a lot of stuff going on here, but let's first write our chemical reaction. So it says 2 molecules of hydrogen. Okay, so 2 molecules of hydrogen. So that hydrogen is diatomic. Okay, so it's H2. React with 1 molecule of oxygen. Okay, oxygen also diatomic, so O2. To produce 2 moles of water. Okay, 2H2O. So here's our chemical equation, and they are giving us the numbers for them. Okay, so 2H2 plus O2 gives us 2H2O. All right, now the question is saying how many moles of water are produced from 2.0 times 10 to the 23rd molecules of oxygen. All right, so what we're going to do is we are starting with 2.0 times 10 to the 23rd molecules of O2. Let's say molecules of O2, okay, oxygen. And they want us to calculate moles of H2O. Okay, how many moles of water are produced? Now, in all the previous problems, we needed to know what's the conversion factor between O2 and water in this reaction. If we look up here, we can see that basically every 1 mole of O2, okay, so there's a 1 here. It's not written, there's a 1. 1 mole of O2 is equal to 2 moles of H2O. Okay, that's what this 2 means. So this is our conversion factor to convert from moles of O2 to moles of H2O. And moles of H2O is what our answer needs to be in. The problem, however, if you haven't noticed yet, is this is, of course, moles of O2 to moles of H2O. And we are not starting in moles of O2. We're starting in molecules of O2. Which means that this conversion factor that we've written out is going to be needed, but it's not the one we're going to start with. We need to first convert molecules of O2 into moles of O2, then we can use this conversion factor. So the other conversion factor then we're going to need to use, and this goes back to chapter 10, is Avogadro's number. And that is that 6.02 times 10 to the 23rd molecules of O2 is equal to 1 mole of O2. Okay, that's our other conversion factor. So this is going to be a 2-step problem. So we're starting with molecules of O2. So the first conversion factor we're going to need to use is this one. Okay, and we're just going to copy paste it up here. Now we do need to make sure that we set this up correctly so that way our molecules of O2 cancel. Okay. Now the way that I've written it, and I know that my font here is really big, so let me make my font smaller so that we're not running out of space. The way that I've written it right now, I have molecules of O2 to begin with, and the molecules of O2 are on the top of the fraction, so that's wrong. Okay, we want to put that on the bottom of the fraction, so we're going to copy and paste this on the bottom. So it's going to be 1 mole of O2 over 6.02 times 10 to the 23rd molecules of O2. Okay, that way molecules of O2 cancel with molecules of O2 here. Okay, so those are going to cancel out. Once we get to that point, then our next conversion will be to convert from moles of O2 to moles of water. And that's where this conversion factor comes into play. Okay, so right now I'm in moles of O2. So the 1 mole of O2 for this conversion factor right here is going to be written on the bottom of the fraction. And the 2 moles of H2O will be written on the top of the fraction. And I know I'm running out of space, so let me make this even smaller, maybe size 14. Maybe we even zoom in on this so we can read it better. Yeah, I guess. Okay. So we are going to be starting with 2.0 times 10 to the 23rd molecules of O2. We're going to divide that by Avogadro's number to cancel out molecules of O2 to get moles of O2. Okay. Then once we have moles of O2, we are going to use the coefficients in the reaction to convert from moles of H2O to moles of O2. Moles of O2 is going to be on the bottom here because we want that to cancel with the moles of O2 that we have right here. And then when we do this, we will get moles of H2O. Okay, so essentially what we're going to do is we're going to take 2.0 times 10 to the 23rd. Okay, so I'm just going to do this on my cell phone calculator here. So 2.0 times 10 to the 23rd divided by 6.02 times 10 to the 23rd, and then multiply that by 2. And when we're all said and done, we get a final answer of 0.664 moles of O2. Okay, that's our answer. All right, and I would usually have done this on paper, but hopefully that makes sense. All right, now that was only the first half of the problem, because the other half of the problem is how many moles of water are produced from 22.5 moles of oxygen. Okay, so the second half of the problem is saying if you have 22.5 moles of O2, how many moles of H2O can you make? So it's just another conversion problem. But the nice thing, at least with this one, is we are already starting in moles of O2. So our conversion factor, which again can be used up here, is 1 mole of O2 will make you 2 moles of H2O. Okay, that's our conversion factor. And again, that is from right here. 1 mole of O2 will make you 2 moles of H2O. And I'm going to write this as a fraction. So let's write this as a fraction. Put in parentheses. Okay, so here's our fraction. We are starting with 22.5 moles of O2. So if we do our dimensional analysis, 2 moles of H2O divided by 1 mole of O2. Okay, since we're starting with moles of O2, we want to have these moles of O2 on the bottom of our fraction. So that way it will cancel with these moles of O2. And the moles of H2O will be on the top, because of course that's what our answer wants. So we're going to take 22.5, multiply that by 2, and that will then tell us how many moles of water we can make. And I get 45 moles of H2O. All right, so that problem was a little bit more challenging, and actually that is going to go more into what the second section of this chapter goes into, but it's just a little bit of a taste of kind of what we're doing. Okay, so basically what we're doing is we're taking all of the stuff we learned in chapter 10 on converting between molecules and moles and grams, and we're taking the stuff from chapter 11, which was writing and balancing chemical equations, and we're essentially just putting it all together, right? So it's not really any new skills, it's just taking old skills we already have and applying them in just kind of a different setting. Okay, so hopefully that helps you. And again, as always, if you have any questions, feel free to reach out to me so that I can help you. All right, guys, that's it for this one, and I'll see you in the next one. Bye.